Hello everyone, you are welcome to Organotope Chem Clinic, where chemistry becomes crystal clear. I'm Temitope Adeniji. In this episode of our general chemistry, we are going to be considering electronic configuration, in which we are going to talk about the identification of the types of subshell, also known as the orbitals. We are going to talk about the order of arrangement of the orbitals in the electronic configuration. We are still going to consider the electronic configuration of atom and ions using the full representation as well as the shorthand form of electronic configuration, also known as the condensed form of representation of the electronic configuration. Towards the end of this video lesson, we are going to be extracting our examples from chemistry past questions. So I will advise you to stay tuned till the end of the lesson. You will love it. What are orbitals? An orbital is the region around the nucleus of an atom where electrons are located. We have 4 types of orbitals in the periodic table, which include the s orbital, the p orbital, the d orbital, the f orbitals. So we are going to be considering the ordering of these orbitals based on their energy level. So we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and so on. So we consider this as the first energy level. This is the second energy level, the third energy level, the fourth energy level, and so on. Here, I'm going to use an arrow to connect the orbitals diagonally. So we have, here is an arrow. Yes, we have this. You can actually make use of a ruler so that you will be able to get the diagonal correctly. Then I will create the bottom of the arrow right here. So we move from the bottom of the arrow to the sharp edge of the arrow right here. So let's consider the order of arrangement of the orbitals for the electronic configuration. From the bottom of the first arrow here, when we move straight down, we have 1s. The next, we have 2s to the tip, 2s. So we move to the third arrow right here. We have 2p, then 3s, 2p, and we have 3s. The next arrow we have 3p before what? 4s. That's right, 3p. Then we have 4s. Okay. The next arrow we have 3d, 4p, 5s. 3d, 4p, and 5s, and so on. So here we've been able to identify the order of arrangement of orbitals in the electronic configuration of an element. Kindly note that each subshell or orbital has a maximum number of electrons it can hold. Now let's take, for instance, the s block has 2 groups. The p block contains what? 6 groups. In the periodic table, we've discussed that in the previous video, so you can check the playlist on the periodic table of elements. So the d block contains what? 10 groups, and the f block contains 14 groups. So which implies that the s block can hold maximum number of electrons, which is what? 2 electrons. So I can write it right here. So 2 electrons. The difference in this orbital is 4 electrons. So we keep adding 4 electrons to the previous orbital. So when we had 4 electrons to 2, we have what? 6. Add 4 to 6, we have 10 electrons. Add 4 to 10, what do we have? Yes, we have what? 14 electrons. So the maximum electron that each orbital can hold is, for s orbital, 2 electrons is the maximum it can hold. The p orbital can hold maximum of 6 electrons. The d orbital holds maximum of what? 10 electrons, while the f orbital holds maximum of 14 electrons. So this maximum number of electrons that the orbital can hold will guide us in writing the electronic configuration correctly. Moving on, I would like us to talk about the electronic configuration of neutral atom, as well as the electronic configuration of the charged atom, also known as ions. We need to understand that for a neutral atom, the number of electrons is equal to the atomic number of that particular element. That is, atomic number equals the number of electrons in that element. When you are asked to write the electronic configuration of an element, you need to understand that we write electronic configuration based on the number of electrons in the nucleus of an atom of that element. While in the case of charged atom, we consider whether the element is losing electron or gaining electron, in order for us to be able to come up with the correct electronic configuration. So we are going to start with electronic configuration of elements in the S block. I'm going to pick an element in the S block, and I will express the electronic configuration of that element. So let's take lithium, for example. Lithium with atomic number 3. Mind you, in most periodic table of elements, the atomic number is always written at the top, while the mass number is written below the elements. But in order for us to avoid any form of confusion, that is the reason why I have to express the atomic number below, so as to express it the way we do for isotopes. Okay, so there must be no confusion when identifying the mass number from the atomic number. Note that the mass number is always higher than the atomic number. I think that is a very good guide for you to understand how to identify the atomic number from the mass number. So back to this, we have lithium with atomic number 3. We need to express the electronic configuration of lithium right here. We have 1s2. Note that the maximum number of electrons that s orbital can hold is 2. So I have to move to the next subshell. We have 2s1. Can we add the electrons together to check whether it is actually a good representation for lithium? 2 plus 1, we have 3. So that is correct. We can pick another element from the P block. We have sulfur right there. Sulfur with atomic number 16. Okay, that implies that sulfur has what? 16 electrons in its shell. Okay, so we have 1s2, 2s2. So we are moving to the P. Maximum electron that p orbital can hold is what? 6. So we have 2p6. Let's go back and add up the electrons. 2 plus 2, we have 4, plus 6, that is 10. So we are still heading to 16. So we have 6 electrons to go. After 2p, we have 3s. 3s, maximum 2. Then after 3s, we have 3p. 3p what? When we add 10 to 2, that is 12. And we are heading towards 16. 16 minus 12, yes, that's correct. We have what? 4. So this is a perfect what? Representation for the electronic configuration of sulfur. So we have from the D block elements right here. Let us pick titanium. Okay, titanium, Ti, with atomic number 22. Okay, we have 1s2, 2s2, 2p6, 3s2, 3p6. Let's try and add it. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, that is 18, we have 4 electrons more. I will go to the next subshell, that is 4s, 4s2, and we have what? 3d2. Why do we have the coefficients of the d orbital lower than that of the s orbital right here? The coefficient of the transition element is always 1 period less than that of the higher orbital right here. So the 4s, after that we have 3d. In an instance whereby we are having 5s, the next will be what? That's right, that will be 4d. Okay, so we've been able to express the electronic configuration for lithium, sulfur, and titanium right here. I'm going to give you a trick to identifying the group and period in which an element belongs to. Okay, now let's look at this. This element ends in s subshell. Okay, we have 2s1, which implies that for lithium, the valence configuration is ns1. Okay, so the n right here indicates the period where the element belongs to. Since for lithium, n equals 2, that implies that lithium is in period 2 of the periodic table right here. This is period 1, lithium is in period 2. Okay, then the exponent of the orbital indicates the group in which an element belongs to. We have S1, which implies that lithium is in group 1. Okay, this shows period. The coefficient shows period. Why the exponents? The exponents give us what? The group. Therefore, lithium is in group 1 of the periodic table. Now, let us consider the p block elements. We have sulfur as an example right here. It ends with the valence configuration 3p4. So the general formula is np4. Okay, now the coefficients right here represent the period in which an element belongs to. So the coefficient here is 3. That implies that sulfur is in period 3. Period 3 for sulfur. And can we check the group in which sulfur is found? Okay, so we have 4 as the exponents here. Recall that the first 2 groups right here represent the s block. So we'll always add 2 to the exponents of every p block element. Okay, so can we check? We have 4 right here and we have 2 to it, which implies that sulfur is found in what? Group 6. Okay, so we have group 6A. Group 6A, yes, sulfur is found in group 6A right here. And we can also express the group as group what? 16. Okay, we have group 16. So the transition elements right here, we have the titanium. The rule that we've considered for the S and the P block element is not applicable to the D block elements. Moving on, we are going to consider the electronic configuration of charged atom, also known as what? Ions. We need to understand that metals, they have the ability to lose electron from their outermost what? Shell. And when they lose their electron, they become positively charged ion. And the positive charge shows that we have gotten what? Loss of electron. For instance, sodium with atomic number 11, when it loses its electron, it becomes what? 10. That's correct. That is, the electron number becomes what? 10. So we are going to have the parent atom, which is the sodium, as 1s2, 2s2, 2p6, 3s1. That is the electronic configuration of the parent atom before what? The loss of electron. Now let us consider Na plus. In Na+, we have loss of 1 electron, which implies that we are writing electronic configuration for what? Yes, that's 10 electrons. We have 1s2, 2s2, 2p6. Okay? So when an atom loses an electron, it assumes the electronic configuration of the noble gas, which is also known as what? The rare gas. Okay? So we can equally say that Na+ has electronic configuration similar to that of what? The neon. Kindly note that the loss or gain of electron does not affect the group and period in which an element belongs to. So the group and period is unaffected because we still have the element as what? Sodium. Elements on this other side of the periodic table, they are mostly what? Non-metals. We've discussed that in the previous video. You can check the playlist for the periodic table of elements. Okay, now we can identify oxygen among these non-metals. Oxygen has the atomic number 8. So in its neutral state, the atomic number is equivalent to what? The number of electrons. Okay, so we can write 1s2, 2s2, 2p what? Yes, that's correct. That's 2p4. So when we add this together, we have 2 plus 2, 4, plus 4. That's what? 8. So this is the electronic configuration for oxygen before the gain of electron. When we have O2 minus, which implies that oxygen has gained 2 electrons to itself, that implies that 2 plus 8, that is 10. Okay, we now have 10 electrons as against the atomic number, which is what? 8. So we are going to be writing the electronic configuration based on the number of electrons that we have and not based on the atomic number this time around. So we are going to have 1s2, 2s2, 2p6. Okay, so here we can deduce that 2 plus 2 plus 6, that's 10. The oxygen 2 minus contains 10 electrons. Now, the parent atom has its coefficients. For the last orbital here, the coefficient is 2, which implies that oxygen is in what? What period? That's correct, period 2. Okay, the coefficient reflects the period. Now, the orbital right here has exponents 4. Okay, recall that we always add 2 for the first 2 groups of the X block to the P block in order to get the group in which a P block element belongs to. Okay, so 4 plus 2, that is 6, which implies that the oxygen belongs to what? Group 6. Okay, Roman numeral 6A. Okay, and it is also the same thing as group what? Group 16. Okay, Roman numeral 6A or group what? 16. In a metal, we do have loss of electron. Loss of electron. Okay, while in the non-metals, we do have gain of electron. When there is loss of electron, there is always reduction in the electron number, which we use to write the electronic configuration. And in an instance whereby there is gain of electron, there is always an increase in electron number, which we use to deduce our electronic configuration. I would like you to check your knowledge on the electronic configuration that we've been discussing. I would like you to pause the video and attempt this question on the board. Alright, let's take the question together. Write the shorthand or condensed form of the following electronic configuration. Indicate their group and period. We can start with this. The number of electrons in this configuration is what? 2 plus 2 plus 3. That is what? 7, which implies that we are dealing with the element with atomic number 7. That is nitrogen, okay? And we need to understand that the noble gas that reflects in this configuration is helium, because it is helium that is contained in this electronic configuration. So we have helium is 1s2. So we can express this helium. Okay, 1s2. So the outermost configuration is 2s2, 2p3. We can also attempt this 2 plus 2 plus 6, that's 10 plus 2, that is what? 12. So the noble gas that is contained in this configuration is neon with atomic number 10. So we write neon. So 2 plus 2 plus 6, that's 10. So this is the valence configuration. We are having 3s2. The next one right here, we are having 2 plus 2, 4, plus 6, 10, 12, 18, 20, 26. So the noble gas that is contained in this configuration is argon. I have argon, Ar, okay? And argon has atomic number 18. Therefore, we have argon right here. So the valence configuration is 4s2, 3d6. Is that clear? On the shorthand form of electronic configuration. So I'm going to take that again from the shorthand form or the condensed form of electronic configuration. Here we have 2 plus 2 plus 3. That is what? 7 electrons. And from the configuration right here, 1s2 is helium. So we are going to write short considering the noble gas in the electronic configuration of the elements. So the noble gas here is helium. So the valence electronic configuration is 2s2, 2p3. Here it contained neon, 10 electrons. So 10 from 12, we are left with 2, 3s2. Here it contains argon, okay, with atomic number 18. So 18 from 26, we are left with what? 8. So we have 4s2, 3d6, okay? Here, to which group and period does the element belong to? Let's take the group. Here we are having group. The configuration here ends with the exponent 3, okay? And it is found in the P block, so you add 2 to it. So the group is group 5A, or group 5A is the same thing as what? Group 15. We have 15. Here we are having the configuration ending with what? 3s2. So this is S block. The group is what? Group 2. Okay? Why this ends in the D block, okay? And the exponent is 6. So we go to D block. 1, 2, 3, 4, 5, 6. The sixth element has group what? Group 8. So the group right here is what? Group 8. Is that taken? The last part is the period. The period is being denoted by the coefficients of the configuration, the last orbital in the configuration. So the period here, the coefficient is 2. So the period is what? We have period 2. Right here, the coefficient is 3. The period is what? Period 3. Here, we are considering the coefficient of the higher subshell, which is the 4s. That implies that the first transition element with the atomic number 26 is in the period 4, okay? So that is on the period of elements in which their electronic configuration has been stated right here. Does that make sense? Here is another question on the board, still on CYK, that is check your knowledge. You have to write the full and shorthand form of the following atom and ions of 26th element of the periodic table. The 26th element of the periodic table is iron. That's correct. So I would like you to pause the video and attempt the question. All right, can we identify the parent atom? We have iron with atomic number 26. So we are to express the full electronic configuration of iron. We have 1s2, 2s2, 2p6, 3s2, 3p6. We have 4s2, and lastly, can we check? 2 plus 2, 4, 10, 12, 18, 20. So we have 6 to go. 3d6. Okay? If we are to express the shorthand form of this, what is the noble gas that is contained in this electronic configuration? That is what? Argon. So I have argon, which ends right here. Argon, so we are left with 4s2, 3d6. Okay? Now for the Fe2 plus, which implies that this is the first ion that we are going to consider here. Fe2 plus, which implies that ion lost what? 2 electrons. So when we have loss of 2 electrons, we are going to be having 24 electrons for the Fe2 plus. But note that electrons are removed from the higher energy level. That is, the 4s electron is exposed to electron loss and not the 3d. Okay, the higher energy level is the 4s, so we expose the 4s to electron loss. Right here we are going to have the full electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6. We have 3d6 and 4s not. So I'm going to expose the 4s orbital to electron loss. And the shorthand form is given as, we have argon. Okay, so the 4s electron is lost. We are left with what? The 3d6. Okay, that is the electronic configuration for Fe2 plus. After we have what? Loss of 2 electrons. It ends with what? 3d6. The 4s orbital is exposed to electron loss. So we have loss of 2 electrons. But in an instance whereby we're having Fe3 plus, so the shorthand form would be argon, and we have 3d5. Because this time around we have loss of 3 electrons. So the one more electron will be removed from what? The 3d6. So we have 3d5. That is the electronic configuration for the transition elements. Note that anytime you are having transition elements, you expose the 4s orbital to electron loss before the 3d orbitals. Make sense? In this video lesson, we've been able to consider the general overview of the electronic configuration, and from there we've been able to talk about the arrangements of the orbitals in the electronic configuration. We also considered the full form of the electronic configuration, as well as the condensed form, which is also known as the shorthand form of the electronic configuration of elements. And from there we've been able to identify the group and period in which an element belongs to. Then also we've seen the order of arrangement of the electronic configuration following this chart right here. So now I want to believe every student can represent the electronic configuration for a neutral atom as well as charged atom or ion. If you find this video lesson so interesting, kindly click the subscribe button and share with your friends right now. You can also follow and like my Facebook page. Thanks for watching.